Rosie?
What? Where do you say it?
Okay, magnetism. So what we're going to do is get our heads around magnetism. So a magnet, when we think about it, when I give you a magnet in the lab, it looks like a red bit of metal. And what we find out by experimenting pretty quickly is if we get two magnets, it depends which ends we put together, how they respond. And so we describe their ends by calling one end a north pole and one end a south pole. And it's kind of like the magnetic parallel of charge. We talked about charge, we had positive charge and negative charge. So with magnets, we've got north poles and south poles. And what's really interesting is that we can't get a monopole. So if you get a magnet, snap it in half, you don't end up with one north and one south. You end up with two little northies-southies. So it's impossible to separate off just a north pole or just a south pole, or impossible. We haven't worked out how to do that yet. And so the way we describe how strong a magnet is, obviously as we get these things closer together, the strength of the magnetic force gets stronger and stronger, either repelling or attracting. And the way we can describe the strength of the force is by talking about a magnetic field. And so the magnetic field we talk about comes out of the north end and goes into the south end. So we talk about this magnetic field and we describe it just by drawing lines. It doesn't make much sense with just one or two, but as we draw more and more, what we start to see is that the magnetic field lines are most compressed together right at the very end of the magnet where they come out. So that's where the magnetic field is going to be the strongest, where those lines are the closest together, and weakest where they're furthest apart. We know that intuitively, that if we have a magnet, the side of the magnet doesn't really do much. It might do a little bit, but there's no strong force there. And you notice that each of these lines has got a direction. These little arrows, these little direction arrows, show us the direction that we would push a north pole. And so if we put a north pole here, it would get pushed away from this north pole. And if we put a north pole here, it would get pulled towards the south pole. And so we've got the same rule that we have for charges, like two norths repel, two souths repel. So like poles repel, but opposite poles attract. So then the really interesting things start to happen when we bring our magnets next to things that are made of other metals. And we discover pretty quickly that some metals our magnet will stick to, whereas other metals it won't stick to. And so the ones that a magnet strongly interacts with are the ones that we call ferromagnetic. And it's like ferro as in iron. That's why iron's Fe on the periodic table. It's ferro. So ferromagnetic, like iron. Iron's the most common one. And so when we bring a magnet close to iron, the iron becomes magnetized. And whichever pole of the magnet we bring close, whether it's the south or the north, the iron becomes magnetized in such a way that it attracts that pole that we bring close. So a magnet will stick both sides, will stick to iron, but then as soon as we take the magnet away, the iron stops being magnetized. And in fact, iron has this cool ability to amplify the strength of a magnetic field. So if we pass a magnetic field through iron, it actually amplifies the strength of the magnetic field, making it stronger than the magnetic field was just by itself. Because all of the little magnetic particles inside iron, they all line up along the lines of the magnetic field that we bring along. Because they all line up along it, they make it stronger and stronger and stronger. So that's the basics